the design because we've already looked at the design in Dr. Khan's presentation, but just to refresh back what crossover design are. So you know that you have study participants, you do a randomization, and this randomization here is not the individual randomization, but it is actually the sequence, right? Because it's the sequence whether these people will get A first and then B, or B first and then A. So it's a little different from, so the randomization is the sequence, how the treatment arms will be allocated to the subject. Okay, that's the important thing that we have to remember. Okay, so I'm just going directly to the analysis part, not really the yeah, the advantage is not okay. So what is the focus is, I said today I'm going to look at only talk about 2 weeks. That means 2 periods, 2 treatments. You can do the same thing extended for n number of NVH crossover with 2 periods crossover. So what is the main objective in crossover design? What are we really trying to see? What are we trying to ask? What is the primary objective? There are intervention works with respect to the control arm. And the control arm can be a standard of care or something that you are all or not giving anything like a placebo, right? So that's the main focus. Randomized by whatever design. Okay. So the main objective here is whether treatment A is better than B, or if treatment A is a new treatment, then B is your comparative arm, and they're trying to see how good the treatment A is in with response to treatment B. So what is the so now when we, and Dr. Khan mentioned about the consort guidelines, the crossover designs, they actually provide you 2 ways that consort guidelines tells you that when you talk about analysis, you have to have either one method, which is called the t-test, which you all know, but I'm going to tell you how this t-test is slightly different from the t-test that you usually look at it in for example, just comparison of means. And then there is another recommended method, which is mainly applicable when you don't have a scale like continuous outcomes. Then this becomes, this t-test is easier. But when you talk about a categorical variable, a binary data outcome variable, then your analysis is slightly difficult when the recommended t-test cannot be used. Okay, and that's what we're going to see. But for continuous and for categorical data, you can apply the other method, which I'm going to talk in a minute. However, for continuous data, earlier days they were using this t-test, and which is still valid even now. Okay? So what did they do is basically, so what, as I said, you are trying to compare treatment A versus treatment B. Okay, and in a crossover design, if you remember the two-way crossover or 2 periods, right? So you have this some subjects who are randomly allocated to the sequence AB, which means that they would receive A first, followed by B. And on the other hand, you have the other group randomized to BA, which means they receive B and then A. All of them are receiving both the treatments, right? That's the advantage of crossover. And therefore, you have many advantages like your sample size is reduced and all. But here, what is important also is that the individual in the trial will also be the control arm, right? So that's yes. So each individual will also act as a control, and that is what makes it more efficient in terms of the variance. Why? Because the variability is reduced. In a panel design, you have each person different from the other, right? So your variability is much more. Whereas here, the same patient who has A and also B, and you're comparing the same patient who received A and B. Okay, so therefore it's only the comparison within the individual, not really like we do in a parallel. So that's why it becomes more efficient. Okay. So what are we actually trying to do? Very logically speaking, is if you have a continuous outcome, let's say today morning you had days of hours of the incubation or whatever. So when you have those as a continuous variable, what are we really trying to say? So we have A. Now I'm the individual who received A as my first assignment, and then I'm getting B. So I receive A, and I know all those response who have received. There is also again B, whether it's the first phase or second phase, doesn't matter, right? Because what are we trying to answer? We only have to answer whether A is better than B. Okay, it doesn't really matter which phase is he getting A or B. Okay, we'll come to that part. The primary objective is to compare A versus B. So what I'm trying to do is, now how is the comparison done? So I'm receiving treatment A, and then after a few days, a few months, there is some change in A, and when I receive B. How do I capture that change? I will take just the difference, right? The change is nothing but how much more or how much less that you are trying to gain in terms of the outcome, which is what your change is talking about. So you capture the difference of all those treatment responses from A and B, and then what you're doing is you have all those who have been assigned to the control arm. So but what are these actually the differences between treatment A and B? Now you do a simple t-test of this change, and that will tell you whether if the response is higher with respect to A or B, you say that there is an improvement, the treatment has worked. So you're just doing a simple t-test, but the only additional manipulation is you're capturing the change in terms of the difference. Okay, that's all. That is exactly what we are doing. We're doing this t-test, but only thing is we're just manipulating a little bit to say what is the change that is happening when I receive A and B, and then comparing between the two arms. Okay. But however, this is simple when you talk about, like I said, outcome variable being continuous. But when you have a categorical, when you have binary data, how do you capture the change? Yes, no, you cannot do that, right? So therefore, to make things simpler, but little complicated also. That's why I always say that you need a statistician for any. So okay. So now when we talk about what is the other way to do it, then, right? So now I'm going to give you a method where the outcome can be a continuous, where the outcome can be a categorical, where it can also be a binary, okay, ordinal, anything. This method can be used, and this is also one of the consult guidelines that has been recommended. So what we are doing is, yeah. Now, yesterday you had a class on cluster randomized. So before we go to the methodology, I just wanted to remind, cluster randomized is what? When you have a group of individuals, instead of one single individual, you are randomizing a village or a family, right? Now, many times, this crossover can also be treated like a cluster. But what is a cluster here? The cluster is the individual. Why? Because I am today receiving A and also B. So there are two time periods where I receive one treatment and the other treatment, but it is coming from the same individual, right? The same individual is acting as a cluster. I can give you one more example. Sometimes you do infection in the eye, right? Or your dental caries. What you do is you take the individual as a cluster, because there are many teeth that you want to study, but they're all coming from one individual and they'll be all correlated. Okay. So that is exactly what we are trying to capture here. So individual is a cluster, but there is a correlation because I'm receiving A and B, and that needs to be here. One the same person is receiving both A and B treatments, so there'll be a correlation, right? Because the way if I'm getting A and B today, and if you are also getting A and B, but the way you respond and way that I respond will be different. Okay, so that is why that correlation we are trying to capture, and that is what we are doing in a crossover design. Okay, so what are we trying to do? So this is what it is. Now a little more advances, there's something called as multi-level modeling, randomized, random intercept model. So what are we trying to say here is, how many of you know match case control? You know case control design? Yeah. So in a case control design, what are we doing? We have cases, the disease individuals, and you have non. You're trying. And you know, a case control design will have too many things, too many confounders that play a role in the bias, right? So therefore, you adjust for them. And how do you adjust? You match the disease with exactly with mostly the main important confounders. You take a control who is matched to the case. Okay, that's how you do a case control. So therefore, what you're doing is you are trying to eliminate all the baseline differences so that you know it's only because of the exposure that this person has been to disease today. That's the same concept what we are trying to apply here as well. What are we trying to do here is, but only thing is here, so what is in way you look at, odds ratios, right? The way you look at odds ratios is AD by BC in usual calculations. Okay, you have odds of disease among exposed, odds of disease among unexposed, and then they get the ratio of the two. Now, the same, you can actually think this of exactly a combination of the case match, case control, and your class. How do we bring both of it? The reason here is, what is the difference? The only difference that the individual is having here is he receives A first and then he's receiving the B. All others, the only thing that we have to worry in a crossover trial is the carryover effect. Okay, you remember the carryover effect, right? So it's not that influence of A is still carried over, but in B, when you talk about the phase 2, then you cannot say whether which is the one which is causing you the response. Okay, so there should be a washout, sufficient washout period, so that therefore there is no carryover effect that is happening. That is the one thing that you need to test before you actually start analyzing your practice. That is what we saw Dr. Khan mentioning, saying that first you do an interaction to see if there is a carryover effect. If there is a carryover effect, then what do you do? Then you cannot do anything because you are at the analysis stage, right? You just report saying that there is a carryover effect, so therefore you don't know what to do. But if there is no carryover effect, then you start analyzing your primary outcome, saying if treatment A is better than B. Now, at this point, I just wanted to say something more about the random.
Oh, under this way there on the piano.
Yes, you can stop me. This is going a little bit difficult. Also, I don't want to confuse you, but just you. So now you have who will see A and B, and there is another person who will see B and C. So this is one group and this is the other group, right? This is how we are analyzing the problem. So what is the only difference I think that is the arm allocated, the sequence, where some will see A and then some will see B as the first period. So all when you say randomization, what you look at your table one, right? Table one is where you provide your baseline distribution and you say your randomization works well. You have large number of observations. Let's say all these are taken care of. So now what you have is you let's say so you have your one. So this is your chain. That means from moving from A to B, this is the whole thing that is done with the response when you see A first and B. Similarly, you have another patient who will also have a slope, right? Who will be with A and B. Now, this is those individuals who started off with B, who will have an average. Focus, they're all aligned. Therefore, this will be a line in this. Now, you also have the other group. Which is the other group? first and then with A. Okay. So now what we are trying to do is, let's imagine this is the average line. Okay. Yeah. So this is another average line, which is some like that. Okay. Now what are we trying to compare is these slopes is what we are trying to compare. Okay. Are you getting the thing? So this is nothing but that intercept. Where is the point which is actually differing? Differing only at the baseline difference. The slopes are the same. The change, the response in terms of the change that is happening when we receive A and B is the same, but what is different for each individual is where this line cuts the y-axis. Okay, you remember in your mathematics, this is your intercept. So he started off with, let's say, 10 units. This person started off with 20 units, and that is what we are trying to construct in a crossover design. So what we do is we take this average of all these intercepts and compare with this intercept, say whether there is a significant difference or not in terms of the
Are we comparing sequence AB versus sequence BA, or actually comparing A versus B?
We are actually doing A versus B, but
if you're having A versus B and there is no carryover effect,
yeah,
then why not just study A and B? Why do we have B and A?
no. The thing
But
is,
they have received A for a period, then B for a period. That's the thing. Particularly when you're studying one drug versus two.
yeah, no. What we are answering is A or B. Okay, the comparison is only done between A and B. But what we are trying to capture is the change for those individuals who went from A to B much higher than those who went from B to A. So,
That's an interaction. So you're looking at an interaction as well. You're interested in the main effect of A versus B, but you also want to adjust for the fact that there may have been an interaction, and that's what you're modeling there, the interaction effect.
So that's why we always saying they're not independent, because there is an interaction which is going on because of the receiving first A and then B, or receiving first B and then A. So I don't know if I have to show all this, but yeah. That interaction is different. That is for the subgroup analysis.
That's for subgroup.
This is the main outcome. This is
Yeah.
your primary objective. So you cannot stop here because you have to answer the question whether A is better than B.
This is not answering the question whether A is better than B, it is telling whether there is an impact or not.
And that carryover effect. There is a carryover effect that you have to worry about. You have the example?
Ma'am, the second line you mentioned, each participant has a the previous slide.
You
Went
went
ahead.
forward and backwards.
Yeah, the slide prior.
Okay.
Previous
Please.
slide.
No, the previous one.
The previous one.
Yeah, each participant has a different baseline.
Mhm.
So isn't it?
Yeah.
Two groups of participants with two different well-defined baselines rather than each individual having a different
Yeah,
baseline.
because that's how. That's what we are trying to see here, right? Because see, when it's easy. See, in crossover design, the efficiency is there because each individual is acting as a control. I'm acting. What we're trying to say. Mine. A and B. Baseline. Yeah. So when you talk about, okay, so they wanted an example of hypertension.
Oh, we'd have to get the data on this. So maybe we can do it at another session because we don't have it prepared right now. No.
We have baseline as another variable.
No. We cannot have a baseline is not another variable. It is baseline is then it's not another variable. So I'll show you an example. Okay, I'll just show you one data. Yeah, then you will understand. So here, if you see, this is ID1, right? Who received treatment A first. Okay, forget about the sequence. He receives A, and then again he's receiving B in the time period 2. The same individual is receiving A and then receiving B. And when he receives A, you have a response that you have measured, right? Yeah, you have to measure. See, that's how the crossover design is. You have to find the treatment response after each period. Okay, so the treatment response after first period, that is what his contribution is. Similarly, you have the ID2 who received treatment B first now, who has a response, and then he received treatment A in the second phase, and then you have a response. So that is how you're capturing. So that means one individual ideally is contributing to 2 observations here. Okay. So, but because they are correlated, right? Because it's the same individual. So you have to capture that correlation. And what we are trying to say is within each individual is A better than B. Within each individual is A better than B. Then what we are getting overall consolidated whether A is better than B. Okay. Putting it all together, that is how we try to answer this. Yeah, you want to say something? Yeah, so this is exactly what we do in a
So after this step, what is the next step? Tell what is A is better than B.
that's what. So basically what as I mentioned to you, in period 1 you have treatment A, right? So all those responses for treatment A you can consolidate together, and then you also consolidate all those with treatment B, and then you compare the difference. But only thing is, what you have to remember is you have to account for the correlation because the A and B are coming from the same individual. Okay? Yeah.
True. The second one, if we assume the y-axis is outcome of interest, would the second graph not go downwards? I mean, would its slope not be negative? If let us say A is better than B, then
No, this I'm talking about all those individuals who may have got B first and then A.
yes, okay. So then one of them, I mean, what I understand.
Yeah, I'm just saying on an average, if this is at the lower level and this is at a higher level, then you know A is better than B.
Can there is interaction slopes can be.
Yeah, you can, because some individuals may be
Make it
doing
better
better
one,
there
yeah.
and some individuals absolutely, but this is the overall treatment is what we are trying to answer. It's not the individual. What I'm drawing there is individually. But then when you consolidate, the only reason I'm talking about individual differences here is there is a correlation which you need to account for, not like the usual analysis of t-test that we do. Okay, that's the only small correction that you have to incorporate. Otherwise, your results will not be the way you want them to be. Okay, you might end up with getting significant. How do you adjust? How do you adjust for the correlation? Now that is
That's
what.
the next one. No, that's the model that she's going to show.
Yeah,
now.
that's a model I'm going to show now. You had something. Because why I said baseline is the only difference here is the baseline, because all others are equalized. When you do randomization, ideally, at least when you have large number of samples, all other confounders are equalized. The only difference now is the baseline. That is exactly what we have captured, because this is the baseline difference, right? For A and B, all others are equalized. The treatment outcomes is basically the differences in the baseline of the individuals, because I am acting as my own control. So I am different from the other.
So maybe to clarify, your baseline is actually all of those rows that are period 1. So you are adjusting for the baseline. It's the effect at period 1.
See, this is the modeling. Basically, there are two issues here. The same individual is used before and after. That is your A and B. Therefore, my information is correlated. So how do you capture that information? That is why that the intercept is very important. The modeling which we do is called the random effect model, where that random means that the intercepts are different across individuals. That gives you the intra-class correlation coefficient, which gets adjusted as we do in the cluster analysis. So
of this treatment than another individual who also received the same treatment. Why is it happening? Because I'm different from the other. That's a baseline difference.
Oh, he's using baseline differently than what she's
Oh, is it?
talking about baseline. She's talking about baseline, doing a value measurement of the response at time 0. We're not doing that. No.
I think you cannot capture
No.
that.
Okay. Now I understand her question. Yeah. Mhm.
Yeah. And ideally, when you're doing randomization, ma'am, the baselines are the same. Baseline data. Okay.
Mm. So I think I understand her question now. So if you have, if you, what you have is if time, you have time here, yeah? So you have time 0, you have time when you measure at T1, and then you measure T2. So somebody enters the study here, time 0, and they are assigned to sequence AB.
Okay.
So at time T1, you're measuring the response at time A. And then at T2, you're going to get the response at time B. So that's when period 1, its response for this number 1 is A, and this is B because he's AB. Somebody else is BA. This is the response at B, and this is the response at A.
Yeah.
What she's saying is that to check for carryover,
You look at the
maybe I
baseline.
should know what the value was here, and that after this, the person goes back to this new time should be similar to that. But if we don't have this measured,
Yes.
we don't have this measured. We just have the responses to the different interventions. But yes, if you had a way of doing it, you could do it.
Exactly. You can include any covariates in your randomized trial because correct. Yeah. Correct.
Mhm.
Is your baseline difference.
Mhm.
No, but the thing is, you don't have to. I mean, what I'm trying to say is, you don't have to check because what we're trying to answer is A better than B? Whatever the check may be. I may be doing very well. Some other person may not be doing very well, but still the treatment response should be better.
No, but what she's saying is that suppose I'm assigned to AB and I get A in the first period, and A works so well that I don't go, when you remove A, I am a new person now, and I'm doing much better. And so my response to B is affected by the fact that I did not. That's when you have an interaction, sorry, carryover effect. But carryover effects, you have to assume there's no carryover effect. What you're asking is, you're demanding that you check.
Let me tell you an example. My systolic BP is 160. I had an antihypertensive A. My systolic BP came down to 120. It was persistent like that. I'm happy. Washout period is over.
my systolic BP is 140 or 130, which is not the baseline. So I'll be giving the other one. So I need to take the data and document. Isn't that the question?
The thing is, you should do a crossover trial in those situations
When
where
you
you
do
can come back to your baseline. Otherwise, you cannot do a crossover trial.
Usually it is not possible.
So it
But it will take the mean now.
Yeah.
Just one more point, I'll stop there. It's the same point that I was trying to say about the p-values at the point.
We did not have the mechanism to look at different cutoffs for p-value. We just went with 0.5. So now we might have mechanisms to incorporate that. So I was just wondering.
You can, that's what, if you can measure the baseline, very well and good. And you have to put that in the model
Yes.
when you talk about. But only thing is, you have to mention that in your protocol before, saying that you have a baseline measurement and then you will adjust for the baseline. But what, I don't know, but what I feel is, there's no need to do because my question is only to answer A better than B.
No, but you're assuming no carryover.
Yeah, no carryover effect.
That is
But
a
if
key.
there
And
is,
she's
there
she's
is a
wanting you to
mechanism where we
show that there
can,
is no carryover.
if there is, like, I believe that because of the advanced methods, there should be something to capture that. Because if you know quantitatively, it's better than just qualitatively saying they are the same. So you can actually look at it quantitatively. That's why we do have statistics. No, that's taking it.
Just go ahead and say that what is sequence effect? What is the meaning of sequence effect?
I think
So
I'll
that
stop
we'll
him,
discuss.
sorry for that.
Maybe that is better. Otherwise, we'll be discussing about this one. The sequence is the one which we assume that there's no carryover. That is
She's not
captured.
talking about carryover. She just says that you measure a baseline and you also adjust for it, which should be much better.
Yeah, I mean,
Yeah, exactly. Yes. Assume.
right.
No, but
But I think that maybe I understand what. No, but what she said is also, suppose my blood pressure here, I know is 160, and it came down to 120. And if I measure it again here before I go that, and it's 130, and then to get the effect of B, and whatever, let's say it goes to 135, then the effect of A is to lower it by 40, and here it is to increase it by 10 if I measure this. But if we don't assume that we're measuring this, we would say the effect of this is this, and the effect of this is this. So you are looking at differences that assume no carryover effect.
yeah.
And but I cannot two people at the same time. Yeah, one at a time is better
Yeah,
because we
because
cannot.
you have to answer, ma'am. It's okay, you can ask.
Yeah. Yeah, show the analysis and then people will understand.
I'm not showing anything, so just showing the
Oh,
output. Yeah.
okay.
So actually, this is what when you do a.
Right.
Yeah, okay. So basically, again, the same question is that you have, this you have understood how the data is organized, right? So you have the first person who's assigned to A first and then B, and then that's the time period 1 and time period 2. So we have just shown you two responses, one in terms of the continuous outcome and one as a binary outcome, okay, just for the purpose of demonstration, right? So what we have to do ideally in a crossover is you have to check for the carryover effect. That is very important to see that there is no carryover effect on the washout. Basically, when I say no carryover effect, it means to say that the washout period is adequate so that you are coming back to your baseline thing, and then you're trying to give the new intervention as a next sequence. Okay. So what we are doing here is, I don't know. Okay. So this is how, so what are the different things that we have to look at? One is, as I said, the carryover effect, and the other one is the treatment. Okay, those are the two things mainly that we have to check for. So first is the carryover effect is basically by the sequence. If you look at the sequence is talking about receiving A first and then B, or receiving B first and then A. Okay. So what do we expect here? What do we expect here is, if suppose there is a carryover effect, right? You then in one, there should be a very high value of the outcome that you see for the sequence as a variable. But if you don't see, or if it is not significant, then you know that there is no carryover effect and the washout period is quite adequate. So therefore, you are in the right track of a crossover design. Okay. Now you can start interpreting what your treatment effect is going to be. So that is the first step. So what we are doing here is, when you look at the outcome, here the sequence is talking about that's the coefficient, and you know the probability. Yeah, thank you. Probability is p-value is 0.663, which means it's not significant, right? Now this is a very hypothetical data. Okay, it so happen that it is very insignificant sign. But what ideally we wanted to say is, if the sequence is insignificant, that means there is no interaction of A and B or B and A, and therefore the washout period is quite adequate, or which means to say that there is no carryover effect of A on B or B on A. So therefore now you are able to start interpreting your actual treatment difference, whether it exists or not. And that is what you see in this variable, which means to say that there is a difference between A and B of 15 units, right? Okay, A minus B. So that means what treatment A, when you receive, there are 15 units on an average more as compared to treatment B, which is also statistically significant. Okay? Yeah. This one. And this is your confidence interval. So even if you look at the 95% confidence interval, it is as low as 22 units, and the difference is also as low as 7 when you talk about the difference between A and B. Okay? Are you clear with that?
Yes, minus sign show that A is better than B.
Exactly. A minus B. However, you have taken capture, right? Like I said in the beginning, when you say it's a positive and if A is higher, then you know that A is actually better, right? But when you take B minus A, and so you should know the direction of how your treatment differences are taken. Okay, that is important. And then but here what we're trying to say is the treatments are different, significantly different. Now when you're interpreting it, you see whether mean of A is higher or the mean of B is higher, and then accordingly say whether A is better than B or B is better than B.
What I would suggest is that
Yeah.
add another in my mind, because here we are forgetting the people.
We are only thinking of the intervention and what can related to the intervention. What is that factor which will factor in the individual?
Yeah, I mean, yeah. Yeah. Yeah, you're assuming that at baseline they were the same, which is in a large sample, they would be the same. And so it's whether you, as Abraham says, you're assuming that on average they're similar. Yeah, I mean, if you had measured it, you could just include it and study the change instead of the measurement. So at the individual level, just like I mentioned before, you can choose as your outcome the mean, or you can choose as your outcome the mean change. It's whatever you want to choose. And if it's meaningful for you, the change, then study the change.
So it's not the count for the baseline, because the change in P as a program there. No, the change from 160 to 130 is not the same as the change from 130 to 130.
Yeah, no, I know.
So those baselines become important. It reflects the individual. So the other is effect of the individual.
Yeah.
So you are counting in this model. You are taking only the treatment. It's not the case.
But see what in all of these studies, we're randomizing, we're assuming that the baselines on average are comparable in one group on the other because we've randomized a lot of people. That's a limitation if you don't, yeah.
To check if that
To check. Right. You have a table one. You'll have table one. Yeah.
Okay, I can do that. Sure, I can do that. So this is basically in theta. I think so. Yeah.
Random effect model. This is a mixed effect model. Is that because the same individual contributed to information, correlated information. We need to adjust for it. That is why we are going for it. Otherwise, you'll do a simple PAT-T test or whatever. To some extent, it adjusts for the baseline data, the PAT-T test. Same individuals used. This tells you whether that the before and after measurements by an individual is correlated or not. If it is very highly correlated, what happens in the information which we don't know. So this is, so where do you, therefore we are using mixed effect model. So you can do it in SPSS also, but this is to demonstrate in data. That is the first reason you just go for the individuals information are correlated. It has to be adjusted for. That is the reason.
Yeah, what the basic idea of doing this crossover is to understand that there is a correlation and we need to account for it, not like the usual t-test that we do, where we just treat everybody as independent observations. Then, yeah, so this is your where you are providing your response, whatever your response is, variable. And here you're giving your treatment and the sequence, which is talking about the interaction term. Here I've just shown it because I put everything together. But ideally, first thing is you have to look at only sequence and see if it's significant or not, and then what is really important is the next step, where you say what is the level that is actually to be correlated. So here it's the individual, right? The ID. So that is what we are trying to say, this one. And what we have to do next is change this one, because when we say independent, it means that the correlation is 0. So they cannot be independent. They're not independent observations. So you choose this one to be unstructured. There are different correlation structures. So you can choose one of them, but not independent. And then that's the step. I mean, the step is the doing it is simple, but why we are doing it?
You interpret the results. Now let's say treatment A is better or B is better. That is very clear. That is significant here. Now we need to discuss whether the sequence A or B, B or A, is it different? If it is different, what does it mean? What does it mean? Sequential effect. It is not there. Okay. So, and mostly the period effect and sequence effect go together. Yes, yes.
Usually you don't look at the period as only to understand whether the first period makes a difference or the second. But that's not what our interest is. Ideally, we are looking at really a sequence and the treatment.
That's the sequence.
That so you compare the two periods. Period one, you take the average response A minus B in period one and A minus B in period two. Compare it. That is period effect.
You also could do another model where you put in the period by treatment interaction to see if the effect of the treatment is different in different periods. So if I get A in the first period versus
So
B versus
can
A
you
in
do
the
that?
second period versus,
This is
In my machine. So I'll give my.
yeah.
So suppose that sequence becomes significant. What do you do?
So when the sequence is significant, that means there is a carryover effect. Say that there is a carryover effect, you produce that in your paper, say that there is a carryover effect, so you don't know.
For certain variables or certain settings, it may not work.
Right.
Yeah, definitely.
So the only thing you could do there, is analyze the first period, because now you don't have the carryover of the first period into the second. And so what people like to do is when they get a significant carryover effect, they still want to publish. So they'll publish the first period and then they'll try to do the second period and then try to do it, more analysis of.
So we publish the first paper, or we don't publish, then take the rest of the data.
Anyway, you're not supposed to do duplicate publications, like it's the same patient, same.
You've already done the study. You are and then write in a new protocol after you've done the study. Yeah, we should stop and then I'll do interim analysis after lunch. Yeah. Okay. Yeah, exam exam. But, yeah, well, I think we should just go for lunch now.
And because if there is influence more, yeah. No, because if there is a sequence, see what I'm trying to say is when A and B, when you look at the magnitude of it, if it is very high and there is significant, that means there is something happening in the second phase where A is carried over and therefore you show that B is also. It's a sequence and carryover is the same because basically when we put it here, we put it as sequence. That's a test for carryover.